So the correct way to pronounce the title is Water Waves Be Curved and Other Tales of the Sea. Need this. So what am I talking about? Basically, I want to put forward that water waves are really curved, and that the cylindrical representation of these curved waves is a good way to represent the wave field around floating bodies. It can be used to efficiently compute the interactions between multiple floating bodies. They can describe short-crested seas, and it's a good way to understand wave energy absorption. So what is a curved wave? Well, a curved wave is not a plane wave, so it's the opposite of this. A plane wave is a sinusoidal wave that has infinitely long crests, and you can create them in a wave tank, or they're pretty easy to create mathematically, but really this is a two-dimensional solution. They're used throughout ocean engineering and ocean sciences because they're easy to understand, and you can use them to create more realistic short-crested seas. But these are curved waves. So over here you see kind of a point source generating curved waves that are propagating outwardly. This is a drop of water creating circular waves. You can't see this very well, but that's supposed to be a short-crested sea. And then this is a video of some experiments that I did here in the curved tank. And it's a flap, a bottom hinge flap that's being made to oscillate back and forth, generating, hopefully you can see curved waves radiating outward from it. So it's difficult to do this without some mathematics. I'll try to be kind of as high level as possible, but there are going to be some equations in here. So it all comes back to the linear wave boundary value problem. And for those of you who aren't familiar with it, just as a simple explanation, we're talking about a fluid, most typically water. We have a flat bottom, we have the fluid, and then we have a free surface, which is the interface between the water and air. And that free surface I'm going to denote as the variable eta, and so you'll see eta a lot as well. In the fluid, we might have a body, there might be a radiation condition. These are harmonic waves, so they're sinusoidal in time. A solution to the linear wave boundary value problem is a plane wave, and that's a solution you get when you solve it in Cartesian coordinates. But this is a particular solution to the boundary value problem. A more general solution you can also get from plane waves by integrating plane waves over all directions, where the amplitude of this plane wave A is a function of the direction beta. But if you solve the boundary value problem directly in cylindrical coordinates, r in the radial direction, theta in the angular direction, and z going upwards, you get a solution that looks more like this. And this solution is kind of the heart of a lot of the research I'm doing. So I'm going to have to explain a little bit more about it. So what it is we're describing the wave elevation as an infinite summation over some terms here. These h's are called Hankel functions, and they describe the wave in the radial direction. And they're just sinusoidal-like functions that kind of decay as you go out radially. They're complex valued. H1 is the Bessel function of the first kind, Jm, plus I, the imaginary number, times Ym, the Bessel function of the second kind. And that describes waves that are coming into the origin. H2 is the complex conjugate of H1, and that describes waves that are propagating outwardly from the origin. In the angular direction, theta, we have sort of an integer sinusoidal dependence. So at m equals 0, we have a wave that's constant as a function of direction. At m equals 1, we go around one oscillation as you go around in direction. M equals 2, you have two oscillations. M equals 3, three oscillations, and so on. When you take the hm terms and the theta terms at a given m, you get what I call a partial cylindrical wave. So the m equals 0th partial cylindrical wave is this wave here, and it's an isotropic wave, so it really describes kind of the wave that's generated by, or would be generated by, a heaving body. At m equals 1, you have a surging wave, so a wave that could be created if you move a body back and forth. For higher m's, you get less physical waves, but the idea is that when you add these partial cylindrical waves together, modified by certain complex coefficients, you can create any linear wave field that you want. So let's talk about the waves around a floating body. So the wave field around a floating body can be described as an incident wave plus waves that are scattered by that body held fixed, plus waves that are radiated by that body moving in each of its degrees of freedom. These scattered and radiated waves can be described by these cylindrical waves. We know that the scattered and radiated waves have to propagate away from the body. This is called the Summerfield radiation condition. And you can just kind of imagine that intuitively. If you move a body, you can't make waves that come towards it. So that means that all the incoming coefficients for H1 are 0, and the wave field is just described by these coefficients for the scattered and radiated wave times the outgoing waves. So the key is for any given body at any given frequency to figure out what the coefficients are. And we did this computationally in a paper that was published in 2003. So here in this top figure, we've computed the entire wave field with the boundary element software WAMET, which is kind of the standard software for computing wave-body interactions. Then we computed just the points around the circular cylindrical surface surrounding the body. And when you integrate over these points and you take a Fourier transform, you can use that to find out what these cylindrical coefficients are. And so the bottom figure is showing a wave field that's produced analytically, where the coefficients AM, SR are found by just looking at this circular cylindrical wave. And then this is showing the difference between these two wave fields, and really they match up, they're identical within linear wave theory. We also did this experimentally. So these were experiments that I was working on last autumn, and it's the same concept. We put a body in the experiments done in the curved wave tank here. We put a body in the tank and then had a circle of wave gauges surrounding the body, measured the wave elevation on this circle and used that to determine what the cylindrical coefficients were, then compared the cylindrical wave field to the measured wave field out along these spokes. So this is one of these tests. This is for, again, it's the flap moving at 1 hertz, radiating a wave. The top figure shows the measured wave and the cylindrical wave around the circle. The red line is actually WAMET, so that's the computed wave that WAMET would predict. The measured wave and the cylindrical wave actually lie right on top of one another, but that's where we generated the cylindrical coefficients, is around that circle. So really what we want to compare are the out along the spokes. And so again, the blue line is the cylindrical wave, this black dashed line is the measured values, and so there is some difference, but generally we can see that this cylindrical wave field does accurately represent the radiated wave field of this flap. Also, these are the magnitude of the actual coefficients themselves. I know this figure is very small, but you can see it's dominated by 2 coefficients, and these are at the values of m equals -1 and m equals 1. And if you remember earlier from the equation slide, I said that at m equals 1, we have a surging type wave. So as this flap moves back and forth, it creates a surge type wave. So once we know how a given body radiates or scatters waves, we can use it in what's called an interaction theory to compute how multiple floating bodies interact with one another. And so the heart of this interaction theory is the concept that the waves that are incident upon this body I are some ambient incident waves that exist in the wave field, plus the scattered waves of all the other bodies J in the array. And once we know what the incident waves to this body I are, we can use this thing called a diffraction transfer matrix, which I think is a really neat operator. But it transforms, it's a property of body I, and it transforms these incident waves on body I into the waves that that body scatters. So the scattered waves of body I are then these kind of other colored waves here, and these are waves that are incident upon the other bodies J. And so you can kind of see how you could take all this information and form it into a large system of equations and solve for all the scattered amplitudes and then find your multi-body array interactions. So this is something that we did. We computed an array completely with Wilmot and then with the interaction theory. And again, they match up perfectly. This is the difference between the two. And then we computed, and so this is an array of these bodies here. So this is like a hinged raft kind of wave energy converter. It has 8 degrees of freedom, the 6 regular degrees of freedom, and then 2 hinges. And then we computed a large farm of 101 bodies, so a total of 808 degrees of freedom, which is a pretty massive problem. And that took about 40 minutes to do in the MATLAB code that we wrote for the interaction theory. And it's a computation that it would just be completely impossible to do directly in Wilmot, which is typically how people have done it. And the idea here is that if you were to do an array computation in Wilmot, say you were going to put 2 of these bodies in Wilmot, this body is represented by, we'll say, 1,000 panels. So then you, in Wilmot, on each panel, you essentially are solving for an unknown variable. So now you have 2 times 1,000 variables to find in Wilmot. Whereas when we do it in the interaction theory, instead of representing this body directly by its panelization, kind of precisely by its geometry, we're instead representing it by its waves. And we really only need 10 to 20 to 30 coefficients to represent the body's waves. So instead of 2,000 unknowns, we have 20 or 40 unknowns. And so that's why it's much, much faster, the interaction theory. So, as I kind of mentioned, for the interaction theory to work, we also need a cylindrical representation of incident waves. So these are the waves that are coming to the body. So going back to this original equation where we have AI times some incoming waves plus AO, with the coefficient for the outgoing waves, when we don't have bodies and we have an incident wave field, the velocity potential has to be continuous throughout the entire domain. But the Bessel function of the second kind, ym, which is the imaginary part of the Hankel function, is singular at r equals 0, so at the origin. When you have a floating body, the singularity is kind of hidden inside the body. But for incident waves, we have to get rid of it. And we do that by setting the incoming amplitude equal to the outgoing amplitude equal to 1/2 times this variable am. And so you add the Hankel functions together, the imaginary parts cancel out, and you're left with am times the real Bessel function. And this is completely analogous to getting a real cosine function by adding 2 complex exponentials. So for incident waves, rather than having a Hankel function, we now have the Bessel function of the first kind modified by some complex coefficients. So you can even represent plane waves with this cylindrical formulation. This equation at the top is known as the Jacobi-Anger expansion, but it just tells us basically what the coefficients are to represent a plane wave with cylindrical waves. So then these wave fields here are showing the plane wave with different approximations of the cylindrical wave. So they're basically different truncation values. When m equals 0, we're just looking at the 0th order cylindrical coefficient. And this is an isotropic wave, and basically it's only equal to the plane wave exactly at the origin. But as we approximate this plane wave by more and more coefficients, we get a wave that's more and more locally like a plane wave. So we want to also do more than just represent plane waves with these cylindrical coefficients. And you can do that too with the appropriate coefficients. You can create these funny curved waves. So we have wave energy that's coming in from the right-hand side, and then at the origin it kind of converges to a peak, a maximum amount of wave energy, and then diverges as it moves further to the right-hand side. And we did this experimentally as well in the curved tank. So you'll see, it is pretty hard to see, but the paddles are moving here, and I think I keep stopping it, but maybe it's just stopping. But the paddles are generating waves that kind of converge somewhere about the middle of the picture, and then the wave energy diverges again. Again, like with the floating body experiments, we measured this wave field around the circle, and used that to compute the cylindrical coefficients, and then compared it to measurements of the spokes. And this, again, this line that's different here, this is what we thought we were making, but what we did make and what we compute with the cylindrical coefficients is exactly the same for this case. And I'm showing you like the best cases of all the experiments, but so you may be saying to yourself, you maybe not, but so what? So those incident waves that you just showed, those aren't any more realistic than a plane wave is. What we really want is a representation of short-crested seas. And this is, I think, where it gets really interesting. So you may be familiar with the plane wave version of short-crested seas, an equation like this where you have a plane wave modified by a complex coefficient. So this is just a summation of plane waves traveling in different directions at different frequencies. And what this really represents is actually an integral. So an integral over all frequencies and an integral over all directions of a random variable A. So here A, rather than being deterministic, is a random variable with a random amplitude and phase. And this random variable is described by a variance density spectrum. So again, this is the variance density spectrum that you're probably familiar with, the power spectrum. But you can have a cylindrical version of this, where instead of being an integral over directions, we have the same summation form that we had before, but instead we have a random coefficient that's also still a function of the frequency. And what gets interesting is when you consider the variance and covariance of these coefficients. So the variance, so the covariance of the coefficient with itself is the integral of the variance density spectrum. And then the covariance between these two, between the m and nth coefficient, is the m minus nth Fourier coefficient of the spectrum. For those of you that have looked at directional spectra or gotten directional spectra data off of a buoy, you know that you don't get like a spectrum as a function of direction. Instead, you get a sort of a variance density, and then you get the Fourier coefficients. And what I find that's really interesting here is that these Fourier coefficients have a direct meaning, that they're the covariance of these different cylindrical representations of the short-crested wave field. So I know that's all pretty abstract, and even for me it's a bit abstract. But to try to kind of show it a little more visually, here we have a directional spectrum. On this axis is frequency, and then this axis is direction. And so in cylindrical form, instead of representing it as this kind of two-dimensional continuous function, what we have is still on this axis a function of frequency, and then for each delta m minus n, we have different covariances. So the m minus n equals 0 is just the frequency spectrum. So the frequency spectrum independent of direction. And then for different m minus n's, you have different covariances between the coefficients. And what this is describing is when the covariance goes to 0, we're almost talking about independent short-crested waves. You're saying that it gives you an idea of the crest length. We can also compute the power in a wave field. So the power of a wave field given by cylindrical coefficients is proportional to the square of the incoming coefficients minus the square of the outgoing coefficients. And that kind of makes intuitive sense. When you have an incident wave and the incoming coefficients are equal to the outgoing coefficients, then the power is 0. But if you have some sort of body in the wave field, rather than representing the outgoing coefficients as the incident, you're actually modifying the outgoing wave by the scattered and radiated wave. And so when you want to absorb wave power, essentially what you want to do, you can't affect the incoming wave, that's just the incident wave, but you want to try to make the outgoing wave equal to 0. And that's how to effectively absorb wave power. So this is something I'm kind of still working on. I don't have a lot of information on this. So in conclusion, curved waves be not monsters of the sea. Water waves are naturally curved. In linear wave theory, the cylindrical solutions are a really good way to represent these curved waves. They can be used to compute floating body wave fields, multi-body interaction, spectral seas, and wave power absorption. And I'll leave you with one final video from our experiments. And this shows one of those focus waves that I described incident upon the flap that's held fixed in the center of it. And the flap reflects the wave energy in a directional form that's almost exactly the same as the focus wave that's coming into it. So you get this really cool curved standing wave, and you can see that the wave is just kind of bouncing up and down right there. And that's it. Thank you very much.
This production is brought to you by the University of Edinburgh.